I am Prasad teaching for 8th, 9th and 10th SSC and ICSE board for the last 34 years. Today in this video, we are going to cover up the basic concepts of the 10th standard chapter number 3, that is circle. Let's start with the topic. First point regarding circle. What is the definition of circle? If I draw a circle, what's its definition? It is a set of points. Circle is a set of points which is equidistant from a fixed point. The fixed point is called as the center of the circle. I denote it by O. And the fixed distance is called as the radius of the circle. Some terms related to circle. First is the chord of the circle. What do you understand by chord? A segment whose end points lie on the circle is called as chord of the circle. Segment whose end points lie on the circle is called as the chord of the circle. So I made chord AB. If this chord passes through the center of the circle, then it is called as the diameter of the circle. If this chord passes through the center of the circle, then it is called as the diameter of the circle. Let's talk about the diameter now. Diameter I made PQ. How many diameters can you draw to a circle? There are infinite diameters that can be drawn to the circle. Diameter is twice the radius. Diameter of the circle is twice the radius. Then let's come to another term. A line intersecting the circle in two distinct points. A line intersecting the circle in two distinct points is called as secant of the circle. Secant XY. Line intersecting the circle in two distinct points is called as secant of the circle. Third point. Tangent. A line having only one point common with the circle. A line only having one point common with the circle. This is point M. This is a line L having only one point common with the circle is called as tangent to the circle. So tangent I've drawn is line L. And a common point is called as point of contact. So which is the tangent? Line L. Which is the point of contact? That is point M. These are the very basic things regarding circle. Next point I move on to. Second point. If I have 2 points, how many circles can be drawn passing through these 2 points? There are 2 points A and B. How many circles can be drawn passing through the 2 points? That is infinite. Infinite circles can be drawn passing through 2 given points. If there is one point M, how many circles can be drawn passing through this one point? Again, infinite. If there are 3 non-collinear points, what do you understand by non-collinear points. If there is no line, single line, passing through three given points, then points are called as non-collinear points. I'll explain it here. If I draw points like this, A, B and C, I can draw a line passing through these three given points. So these points are called as collinear points. And if I make the points like this, A, B and C, there is no line passing through these three given points. So that is why they are called as non-collinear points. How many circles can be drawn through these three non-collinear points? Only one circle. One circle. How many circles can be drawn passing through these three collinear points? No circle. Now here, once again we'll have a review of it. Set of points equidistant from a fixed point is called as circle. The fixed point is called as center of the circle and the fixed distance is called as the radius of the circle. Segment whose end points lie on the circle, chord of the circle. Chord passing to the center of the circle, diameter of the circle. A circle has infinite diameter. Diameter is twice the radius. A line intersecting the circle in two distinct points, secant of the circle. A line having only one point common with the circle, tangent to the circle. The common point is called as point of contact. Then the next. If there are two given points, how many circles can be drawn passing through two given points? Infinite. If there is one point, how many circles can be drawn passing through this one point? Infinite. If there are three non-collinear points, how many circles can be drawn passing through these three non-collinear points? Only one circle. If there are three collinear points, how many circles can be drawn passing through these three collinear points? No circles can be drawn passing through it. Now the next point we move on to point number 3, that is tangent theorem. I'm starting with the third point, that is tangent theorem. This is a circle, center of the circle, line L is a tangent to the circle at point M, and OM is the radius of the circle. OM is the radius of the circle. So what's the given part? O is the center of the circle. Line L is tangent to the circle at point M, and OM is the radius of the circle. That's a given. What to prove over here? To prove that OM is perpendicular to line L, meaning the tangent is perpendicular to the radius at the point of contact. Again, I repeat the theorem. What is tangent theorem? Tangent is perpendicular to the radius at the point of contact. I did make a right angle over here because that thing I have to prove it. What has to be proved need not be marked. This is just a tangent. Radius and tangent is perpendicular to the radius at the point of contact. So the angle formed over here is a right angle. That's called as tangent theorem. Fourth one, converse of tangent theorem. This is a circle, center of the circle, OM is the radius of the circle. At the outer end of the radius, I draw a line, and this radius is perpendicular to the line. This radius is perpendicular to the line at the outer end. And to prove that this line L is tangent to the circle. What to prove over here? To prove that line L is tangent to the circle. If you see over here, I have marked over here 90 degree. That means the radius is perpendicular to the line at the outer end. And that is why we can say that this line is tangent to the circle. If you see both of them together, tangent theorem and converse of tangent theorem. In tangent theorem, this is a tangent, this is a radius, and that is why the tangent is perpendicular to the radius at the point of contact. We have to prove that this is a right angle. Converse of tangent theorem, the circle, center, a line is drawn at the outer end of the radius, that is at point M. This is a perpendicular to line L, the radius is perpendicular to line L. That is why line L is tangent to the circle. Whatever is to be proved is never marked. So this is to prove OM is perpendicular to line L. I have not marked this as 90. Here this is given 90 degree, that is why I marked it. And I have to prove that this line L is tangent to the circle. Next, point number 5, I move on to now. That is tangent segment theorem. It is tangent segments theorem, segment theorem. This is a circle. O is the center of the circle. Point P is in the exterior of the circle. From the point P, tangents are drawn to the circle. Which are the tangents drawn to the circle? PM and PN are the tangents drawn to the circle. If you look at it properly, O is the center of the circle. P is a point in the exterior of the circle, and PM and PN are tangents drawn to the circle at points M and N. So this PM and PN are the tangent segments. PM and PN are the tangent segments from P to M and P to N. We don't have to extend it further. We have to, while drawing, we have to do the extension. But when we say tangent segment, we are just talking about PM from P to M and PN from P to N. What to prove over here? To prove that PM is equal to PN. That means if PM is 5 centimeter, then PN will be also 5 centimeter. What does the theorem say? Tangent segment theorem. Tangent segments drawn from an external point to the circle. Tangent segments drawn from where? From an external point to the circle are equal in length. That is called as tangent segment theorem. Point number 6. I'll talk about touching circles. This is circle with center P, and this is another circle with center Q. They have got a common point M. Two circles touching each other at point M, that is having common point M, are called as touching circles. Look at this figure now. This is another circle with center M. Circle with center N. These two circles also touch at point P. That means they have one point in common. So they are called as touching circles. These are specifically called as externally touching circles. Externally touching circles. And these are called as internally touching circles. And the common point, here the common point is M, here the common point is P, that is also called as point of contact. The common point is called as point of contact. If I draw a line passing through the point of contact, this is line L, drawn passing through the point of contact, line L, drawn passing through the point of contact. This is called as common tangent. This is called as common tangent. A line drawn passing through the point of contact of the touching circles is called as common tangent. Next thing we move on to theorem of touching circles. Here I have told you what are touching circles. Now we will talk about theorem of touching circles. What is theorem of touching circles? Point of contact of the touching circles. Point of contact of the touching circles lies on the line joining their centers. What did I say? Point of contact of the touching circles lies on the line joining their centers. Joining their centers. Meaning, here if you see, all this P, M, Q are collinear points. Here M and P are collinear points. That is theorem of touching circles. Point of contact of the touching circles lies on the line joining their centers. That means here points P, M, Q are collinear. Here points M and P are collinear. That is why if I tell radius of this circle is R1 and radius of this circle is R2, what will be the distance between P and Q in externally touching circles? As the points are collinear, I can say that the distance between the centers of the circles over here will be R1 plus R2. Very important. Distance between the centers of externally touching circles is R1 plus R2. Here, if you talk about internally touching circles, radius of the bigger circle is R1 and radius of the smaller circle is R2. Then what will be the distance between point M and N, that's centers of the circle, will be R1 minus R2. This is R1 minus R2 will give the distance between points M and N. So when it comes to externally touching circles, distance between their centers is R1 plus R2. When it comes to internally touching circles, the distance between the centers will be R1 minus R2. Why I can come to this result? Because the point of contact of the touching circles is collinear with the centers of the circle. Point of contact collinear, lies on the line joining the centers of the circle. Next point, I move on to the 8th point, arc of the circle. This is a circle with center O. I'll draw a secant AB. A secant divides the circle into two parts. Can you see, this is one part and this is another part. Each part, this is one part, each part including the common points of the circle and the secant. These are the common points of the circle and the secant. This part and this part, including the common points of the circle and the secant, is called as arc of the circle. So this part is the arc, this part also is the arc. Now how to name the arc? To name the arc, we can write just two letters, or we can write 3 also, but 2 here will not be enough, because if you have to name this arc, this will be arc AB, this also will be arc AB. So which arc we are talking about will not understand. So take one extra point on the arc, X here and Y here. So this arc, I'll name it as arc AXB. And this arc, I'll name it as arc AYB. Now one more thing regarding this. If you look at this arc AXB, this arc has the center in it or no? Center is there in this arc. So it's called as the major arc. So arc AXB is the major arc. And this arc does not have the center, so it will be called as the minor arc. Arc which has got the center, major arc, and the other one is called as the minor arc. Now the next point we move on to, point number 9, that is central angle. Ninth point, central angle. Circle with center O. This is angle AOB. Angle AOB, the vertex of the angle lies on the center of the circle. When the vertex of the angle lies on the center of the circle, then it is called as central angle. Angle AOB is the central angle. And this arc AYB, AXB is the corresponding minor arc. So for the central angle AOB, arc AXB is the corresponding minor arc. 10th point. In that first, measure of a circle is equal to 360 degrees. If we take the measure of entire circle, its measure is 360 degrees. If you want to find the length of the circle with radius r, then the length will be given by 2 pi r. That's a perimeter or the length of the circle. but the measure of the circle is 360. Measure of semicircle will be 180 degree. Third point, measure of the central angle is equal to the measure of corresponding minor arc. I repeat, measure of central angle is equal to measure of corresponding minor arc. Measure of corresponding minor arc. That is, measure angle AOB equal to measure arc AXB. So if I say measure arc AXB is 60 degree, measure angle AOB will be also 60 degree. If I say measure angle AOB is 50 degree, reverse order. So what will be measure arc AXB? 50 degree. Then what will be the measure of this major arc AYB? Fourth point. Measure arc AYB, the major arc, is 360 degree minus the measure of arc AX. So again, if I say this angle AOB is of 60 degree, so what will be the measure of the arc AXB? 60 degree. What will be the measure of arc AYB? That is 360 minus 60, that will come to 300. So that is regarding the measure of the circle, semicircle, measure of the central angle, and the measure of the major arc. Next point. Point number 10. 10 is over, 11 will go. Arc addition property. Arc addition property. This is a circle, center O. I'll take some points on the arc, on the circle, not arc, the circle. I'll take some points on the circle. Now if I want to find out the measure of arc ABP, measure of arc ABP, how I'll get the measure of arc ABP? Will be measure arc AXB plus measure arc BYP. Suppose this arc AXB, the measure of arc AXB is of 60 degree and measure of arc BYP is of 50 degree. Then what will be the measure of arc ABP? That is 110 degree. We can add the measure of these two arcs only because they have a common end point. Arc AXB and arc BYP have got a common end point B. That is why we can use arc addition property. We cannot add the arcs like this. Arc AXB plus arc XYB is equal to arc ABY. That cannot be done because they don't have common end points. But here arc AXB and arc BYP can be added to get arc ABP because they have common end point B. Arc AXB and arc XBY cannot be added because they don't have common end point. 12th one. If this is one circle, center, these two chords of the circle are congruent. Chord AB and chord CD are congruent. I am telling you the chords are congruent. If the chords are congruent, then the corresponding arcs are also congruent. If chord AB is congruent to chord CD, then arc AB will be also congruent to arc CD. If the chords are congruent, the corresponding arcs are also congruent. This is for one circle I am talking about. But if there are two different circles, circle with center P and circle with center Q, I cannot just take any circles. The circles have to be congruent. So circle with center P and circle with center Q are congruent circles. What do you understand by congruent circles? Circles having equal radii are called as congruent circles. So these are two circles which are congruent. What do you mean by congruent? They have equal radii. And in those circles, if these two chords are congruent, then the corresponding arcs are also congruent. That means if chord AB is congruent to chord CD, arc AB will be also congruent to arc CD. I'll combine this and say, in the same circle or in congruent circles, congruent chords are there. If the chords are congruent, then the corresponding arcs are also congruent. Again, in the same circle or in congruent circles, if the chords are congruent, then the corresponding arcs are also congruent. Converse is also true. What's the converse? In the same circle or in congruent circles, if the arcs are congruent, arc AB congruent to arc CD, then chord AB will be congruent to chord CD. These are the two different things I have told, main theorem and the converse also I have said so. Then let's go on to the 13th point. Now the next point, point number 13. I move on to inscribed angle. Inscribed angle. Circle. This is angle. Center can be anywhere. Center here, anywhere here. Angle can be here also. Anywhere you can draw the angle. Center is here. This is angle ABC. I am talking about inscribed angle. Angle ABC is inscribed in arc ABC. Now, why this angle ABC is called as inscribed angle? Because its vertex lies on the arc and the end points of the arc lie on the sides of the angle. Why angle ABC is called as inscribed angle? Again I repeat, because the vertex of the angle lies on the arc and the end points of the arc lie on the sides of the angle. Now if you look at this diagram, this circle, center, if I draw like this, angle PQR if you say the end points of the arc lie on the sides of the angle, so is angle PQR the inscribed angle? No. Why not? Because the vertex of the angle does not lie on the arc. So both the criteria should be fulfilled. Vertex of the angle should lie on the arc, and the end points of the arc should lie on the sides of the angle. Then we can say that angle ABC is inscribed in our ABC. 14th point, I move on to intercepted arc. I take the same figure. If you look at this arc AXC, end points of this arc lie on the sides of the angle. This arc. End points lie on the sides of the angle, and all the other points on this arc lie in the interior of the angle. That is why this is called as intercepted arc for angle ABC. End points of the arc lie on the sides of the angle, and all other points lie in the interior of the angle. So it's the intercepted arc for angle ABC. Let's look at this figure. Is this the intercepted arc for angle PQR? The answer is yes. Why? Because the end points of the arc lie on the sides of the angle, and all other points lie in the interior of the angle. Though the angle is not inscribed in the arc of the circle, but this is still called as the intercepted arc for this particular angle. This angle is inscribed in this arc, and this is its intercepted arc. This angle is not inscribed in the arc of the circle, but still arc PXR is the intercepted arc for angle PQR. If I draw a diagram like this, this is angle ABC. Is angle ABC the inscribed angle? Answer is no. Vertex doesn't lie on the arc. Then what about the intercepted arcs? There are two intercepted arcs over here. Arc AXC and arc PYQ. Because the end points lie on the sides of the angle, and all other points are in the interior of this angle. End points lie on the sides of the angle, and all other points are in the interior of the angle. So from this it's very clear, though the angle is not inscribed in the arc of the circle, there can be intercepted arcs of the same circle. So with this, we come to the end of the video. There's more to say regarding the basic concepts, but that will cover up in the next video. I am running Prasad's for Learning and Perfection at Goregaon East, Mumbai and Marine Lines, Mumbai. We are having classes for the 8th, 9th and the 10th standard SSC board as well as the ICSE board. I am in this field personally for last 34 years, and we have teachers teaching different subjects, as we have all the subjects for all different standards, and all the teachers are well experienced teachers, and they have the experience of 25 years to 30 years. So much experience the teachers are. If you wish to contact me, the number is given in the description. You can WhatsApp me or you can phone me and wait for my next video. Thank you very much.